let's take a look at the second method, which is the elimination method. And again, rather than reading these directions, I'm just going to walk you through it. So in order to do this method, first off, you're going to choose this method when it would not be easy to solve for either x or y because there's coefficients other than 1 in the front. So if I solved for x or y, I would end up with fractions, and then that makes for a very messy substitution. So we don't want to do that. So instead, what I'm going to do is I'm going to go on the premise that I am allowed to multiply both sides of an equation by the same number and not change that equation's value. You learned that when you were first learning to solve equations. So what I'm going to do is I'm going to multiply this equation by 3, I'll explain why in a minute, and this equation by 2. My goal is to either get my x's to have the same coefficient except one a plus, one a minus, or my y's. Now I chose to get my y's to have the same coefficient, with one being plus and one being minus. So watch what happens, and I'll continue to explain. 3 times 5 is 15x. 3 times negative 2y minus 6y. 3 times 4 is 12. Now I multiply the second one by 2, and I have 4x plus 6y equals 26. Now I want you to notice something. My y's have the same coefficient, but one is a plus and one is a minus. That was my goal. That's why I multiplied the top one by 3, because I knew I was trying to turn that into a 6, and that if I multiplied it by 3 and this one by 2, they would both be 6's. Why would I want to do that? Because now I'm going to add the equations. Yes, you're allowed to do that. Getting a third equation, and the y's are going to go away. So 15x plus 4x is 19x. A negative 6y and a positive 6y is a 0. So I accomplished my goal of getting rid of one of the variables. And then over here I have 38. So now I can easily solve for x by dividing by 19. And I found the first part, the x part, of my point of intersection. Now, unlike the substitution method, I don't now have a handy way to plug this back in and find y. I do have a way, but it's not quite as handy as it was with substitution. So I can choose either one of the equations, plug the x in, and solve for y. I'm going to choose the top one before I multiplied by 3. So it would be 5, take out the x, put in a 2, minus 2y equals 4, or 10 minus 2y equals 4. Subtract a 10 from both sides, and I get negative 2y equals negative 6. Divide by negative 2, and we end up with y equals 3. So the y part of my point of intersection is a 3. And we did that using the elimination method. So again, your goal is to get the coefficient of either the x's or the y's to be the same number but opposite sign. So they will cancel each other out, making a 0, and then you can solve for the other variable. So let's look at example 2. We're going to do the same thing here, but this one's a little odd in what happens. So looking at this, I think I'd like to get rid of the x's this time. So I'm going to multiply my top equation by 2. I don't need to multiply my bottom equation by anything, and that's okay. The top equation is going to now be 2x plus 6y equals 8. And the bottom equation, as it stands, is negative 2x minus 6y equals 3. So I've accomplished my goal of being able to eliminate those x's. So 2x minus 2x. Unfortunately, by doing that, I also eliminated my y's. And I have a 0 on this side, and I have 8 and 3 is 11 on that side. Well, I want you to take a look at what that says. 0 equals 11. When is that true? That is never true. Now, the words never true are not the solution here, but they will get you to the solution. If you get something in your equation where both the x's and the y's make zeros and you end up with something ridiculous like 0 equals 11, we know that's never true, and the reason is because my two lines never intersect. In other words, there is no point of intersection. What kind of lines have no point of intersection? Parallel lines have no point of intersection. So what I would be looking for are those two pieces of the solution. I got something ridiculous, so there was no point of intersection because the lines are parallel. Now, I'm not going to do a third problem, but sometimes you might get something in this kind of odd instance where you would get, instead of 0 equals 11, you would get, say, 11 equals 11. Well, when is that true? That's always true. And the reason it's always true is because my two lines always intersect, meaning if they always intersect, my two lines lie on top of each other. So then those would have infinite points of intersection because they are the same line. So if your x's and your y's both end up making a 0 in the substitution or the elimination method, then it's either going to be this scenario where you got something ridiculous and there's no point of intersection and they're parallel, or this scenario where you got something that's always true, meaning they always intersect, so there are infinite points of intersection and they are the same line.